So I was asked a question during a job interview. What happens when you type google.com in a web browser? And it had me thinking that I should definitely make a theory video on this so that if you're ever in a job interview and this question comes up, that you know how to nail it. I'm going to go deep dive. As you can see, there's heaps of info. But really what I want you to do is I want you to remember the stages because I've broken it down into different layers, different stages, so that in an interview, you just touch on the key topics. So you'll touch on URL parsing, DNS lookup, TCP handshake, for example. But if the interviewer probes you and wants you to deep dive into the concepts, then you also know the technical theory behind it as well. So to begin with, when you come with this question, there's two main sections that you need to talk about. Local device execution, the physical typing on the keyboard, and you also have the network protocol execution, what happens on the website, for example. So with local device execution, the first stage is keyboard and the physical pressing. So for example, beneath your key caps sits a grid of circuits called the key matrix. When you press the G key, it physically pushes down a switch, closing an electrical circuit at a specific intersection of a row and a column. And then you have the keyboard controller, a tiny microcontroller inside your keyboard that constantly scans this matrix. Detecting the closed circuit, it identifies which key was pressed and translates it into a binary number called a scan code. The keyboard controller packets this scan code and transmits it as electrical voltage drops or radio frequencies, if wireless, down the USB cable to the motherboard. Here's a design image of what this looks like. The key things to take away here is the keyboard matrix and the physical pressing. Then we have the motherboard and the interrupt request, IRQ. So the USB host controller on your motherboard receives the packet and extracts the raw scan code. The hardware cannot wait for the CPU to leisurely check if a key was pressed. The USB controller fires a physical signal called an interrupt request directly to the CPU. The signal tells the CPU, stop what you're doing immediately, a human is interacting with the machine. I've put an image of the different components in a PC as well, just for your reference. Key things to remember here. So first you have the keyboard matrix, then you have the motherboard and interrupt request for the CPU. Once it's at the CPU, we also have the kernel processing as well, the brains. So the interrupt vector table, the CPU passes its current execution threads, saves its current architectural state to memory, and looks at the IVT to find the memory address of the keyboard device driver. The CPU executes the driver's ISR code, interrupt service routine. The driver reads the raw scan code from the USB controller's register. The OS kernel takes the raw scan code and maps it against your active keyboard, e.g. QWERTY, translating the raw hardware scan code into a standardized character code like ASCII or Unicode. Summary: CPU pauses, looks at the IVT, interrupt vector table, executes the driver's interrupt service routine, and then scans the code into standardized character code. So far, keyboard matrix, motherboard, interrupt, CPU, and kernel processing. Final stage is handing off to the operating system and browser, the software boundary. So the OS event queue, the kernel places this character into the OS Windows Manager event queue. The operating system checks which window currently has active focus. Seeing that your web browser is active, it posts a message like wm_keydown in Windows directly to the browser's process thread. The render loop, the browser receives the event, accepts the character into its address bar user interface component, and requests the rendering engine to paint the letter G on your monitor screen via your GPU, graphical processing unit. So these are the flows from devices to kernels to applications. This is a question I had when I was writing these notes. What is the difference between a shell, for example, CMD, and the kernel? So the difference really is that You want to look at the operating system as 3 layers. So you have the user, which is you. You want the computer to do something like list the files in a folder. The shell, cmd/a terminal. Kernel is too complex to interact with directly, so it wears a shell to protect itself. CMD is a text-based shell. When you type directory or make directory, CMD takes that text, figures out what you want, and translates it into a formal request, a system call for that kernel. The kernel receives the request from CMD, goes down to the physical hard drive hardware, grabs the data, and hands it back to the CMD to display on your screen. The graphical equivalent, if CMD is the text-based shell, Windows Explorer, Visual Folders, Desktop, and Icons is the graphical shell. Both CMD and Windows Explorer do the exact same thing. They take your input, whether it's a typed command or a mouse click, and ask the kernel to actually do the heavy lifting with the hardware. So that's the physical side. There's 4 stages you want to keep in the back of your mind if this question is asked. Keyboard matrix, motherboard, and interrupt requests, CPU and kernel processing, and then finally the handing off to the operating system and the browser. Now this part, the secondary part, is probably what they're looking for. You want to keep the local device execution in your mind in case they probe you on that side of it. But as a cybersecurity student, the network protocol execution is the most important part, and this is the part you really want to deep dive and watch over and over to really understand. So, as you will see when we're going into it, I've also talked about the OSI model in a previous video called Networking Fundamentals. So if you don't know what the OSI model is, you want to check that out first. But pretty much it normally goes by 7, 6, 5, 4, 3, 2, 1 in terms of layers. But you see here, we actually do layer 7, then 5, then 4, then 6, instead of the traditional sequence. So the reason that we do that is that the OSI model is a conceptual framework designed from the perspective of a data packet moving top down, application due to the physical. Where data formatting and encryption, layer 6 must logically happen before the data is sliced into transport segments. However, in real-world TCP/IP execution sequence, encryption cannot take place until an active network session is opened. Therefore, we must run the lower layer plumbing DNS at layer 5 and TCP at layer 4 first to build the physical pipeline before the TLS handshake layer 6 can pass the keys to encrypt it. So technically layer 6 is happening before 5 and 4, but you need to create the plumbing as used in the scenario to make sure that you can execute layer 6. So the OSI model dictates how data is packaged, but the real world dictates how connections are built. You can't lock a door, layer 6 encryption, until you've actually built the house and the hallway leading to it, layer 5 DNS and layer 4 TCP, which I will go through throughout this video. So the first thing that you want to talk about, what happens when you type google.com into a web browser, is you want to remember that you start at the application layer, layer 7. This layer handles the direct user interaction with network software and initial request policies. So the first thing that we have at this layer is URL parsing and protocol selection. The browser breaks down the typed URL, google.com, sanitizes the input. It automatically defaults to HTTPS port 443 as the baseline protocol. It cross-references the domain against an internal cache of the Safe Browsing API to ensure that the site isn't a known phishing or distribution vector. So for example, you normally type example.com, but you'll see a bunch of other things as well. So the port 80 is normally HTTP, but HTTPS is 443 as we talked about before. Path, query parameters, and fragment / anchor. So if you've ever done web development, you would have known this as well. Once you've done that, once you've done URL parsing, you do HSTS check, the local security gate. If you explicitly typed an insecure HTTP address, the browser blocks it from hitting the network and forces an internal redirect to HTTPS. So pretty much in this diagram, we type HTTP abc.com, but we get redirected back and it changes to HTTPS, which is the secure modern version of HTTP. What are the differences? Well, HTTP does not use TSL/SSL, which I'll describe in a bit, and it sends plain text data, receives unencrypted data, and sends requests and responses without owner and intent verification, right? So it does the same things as HTTPS, but without the security. Now, what does HTTPS do? It transmits data using encryption, digitally signs requests and responses, and it verifies ownership and intent of online requests and responses. So we've gone from layer 7, URL parsing, and HSTS check. Then I want you to remember, we go to session layer 5 rather, the layer that manages the establishment and termination of the logic sessions needed to resolve network names. So what does this mean? I want you to talk about the DNS lookup, domain name system. The core role opens a temporary session to translate human readable names, google.com, into machine routable IP addresses. How does it work? So it goes through a resolving name server, which is normally from your internet service provider. Then it goes to a root name server, TLD name server like .com or .net, authoritative name server, a DNS hosting provider, goes to the records, finally to the web server and site files, finally back to your PC. DNS EC and DOH protection. So the threat is, so if you can include threats that happen at these layers, it will sort of boost your credibility a bit because they're always looking at the cybersecurity angle. They're not just looking at the what's actually going on. They want to know why it's important from a cybersecurity perspective. So when you talk DNS, the main threats are DNS spoofing and cache poisoning. And an attacker injects forged DNS data into a resolver's cache. As a result, when a user types google.com, the poison resolver routes it to a malicious IP address instead of Google's real server. The defense is DNSSEC. DNS security extension adds cryptographic signatures to existing DNS records. The recursive resolver verifies these signatures against a trust chain, proving that the DNS record hasn't been altered in transit. The defense, DNS over HTTPS. This is another defense as well. So you can either talk about DNSSEC or DOH, whatever is more comfortable, it comes to your head first. Encrypts the raw DNS queries by wrapping them inside a HTTPS session, moving the traffic up to layer 7. This prevents local eavesdropping or ISPs from tracking which domains you are looking up. So we've done layer 5, then we go down to layer 4, which is the transport layer. This layer provides reliable end-to-end host communication and data segment flow control. Here, layer 4, I want you to talk about the TCP handshake. Because HTTPS relies on flawless data delivery, it uses TCP, Transmission Control Protocol, which I also touched in that video as well. Before any web data can be sent, a reliable virtual circuit must be opened using a 3-step sequence. SYN, synchronized. Your client machine generates a random initial sequence number and sends a packet within the SYN flag to Google's IP on port 443. SYN acknowledged. Google's server receives the request, notes the sequence number, generates its own initial sequence number, and replies with a packet containing both the SYN and acknowledge flags. And finally, acknowledge. Your client, which is your client machine, receives the SYN ACK and replies with a final ACK packet. With this final step complete, the socket connection is officially established and a reliable sequence tracked pipeline is open. SYN flood mitigation. SYN flood distributed denial of service attack. This is a classic resource exhaustion attack. An attacker sends a massive wave of SYN packets using spoofed IP addresses. Google's server responds with a SYN ACK and keeps memory slots open, awaiting for the final ACK. Because the IPs are spoofed, or you can think of them as hoaxed, the final ACK knowledge never arrives. The server's connection queue fills up completely, causing a denial of service for legitimate users. The defense, SYN cookies. To mitigate SYN floods, modern operating systems and firewalls use SYN cookies. Instead of allocating server memory immediately upon receiving a SYN packet, the server encodes the connection data inside the server's choice of ISN in the SYN ACK reply. Only when a legitimate client sends back a valid acknowledgement does the server validate the math and open a slot in memory. Really important. So I definitely want you to, these 3 things, URL parsing, DNS lookup, and TCP handshake, has to be just, you can be able to recite it off the top of your head, the very common cybersecurity terminology. Finally, in the first half of the steps, we go back to the presentation layer, and this layer handles data formatting, cryptographic negotiation, and encryption decryption. So we have the TLS handshake, cryptographic layer. Once layer 4 opens the pipe, layer 6 negotiates the security parameters via TLS, transport layer security. This is a hybrid encryption process combining fast symmetric encryption for data transfer with secure asymmetric encryption for the key exchange. The client, hello. Your browser sends a packet listing its capabilities, supported TLS versions like TLS 1.3, and a list of compatible cipher suites, combinations of cryptographic algorithms for key exchange, encryption, and hashing. The server hello and certificate. Google's server selects the strongest mutually supported cipher suite and responds with its X.509 digital certificate, which contains Google's public key. Then we go on to certificate validation and cipher suites. Your browser checks its local root trust store, pre-installed by the operating system/browser, to verify the certificate's digital signature against a trusted certificate authority, CA. So Google sent you its CA, so you just gotta, or it sent you its digital certificate, and then we have a certificate authority, which we check that on. It also checks the expiration dates and CRL, certificate revocation list, to ensure it hasn't been revoked. Key exchange. Using an asymmetric algorithm like ECDHE, elliptic curve Diffie-Hellman ephemeral, which I made a video on titled Impossible Math Problem. So you should definitely look on Diffie-Hellman as well. The client and server exchange public parameters. They calculate a shared symmetric session key without ever passing the actual key over the wire. With the session keys generated, all subsequent data sent down from the application layer is encrypted here before hitting the transport layer. So TLS handshake, TCP, DNS, URL, 4 really important concepts that might get quizzed. But again, when you're going through an interview, you've got to summarize this in maybe 90 seconds to 2 minutes. You just touch on these key headings. So you have URL passing, then we go to this stage, then we go to this stage, and then they might be like, all right, explain the three-way handshake, which actually happened in the interview. So then you got to be able to dive into that. What does DNS stand for? And then you should be able to explain that as well. And then the added bonus that I like to include is the threats, right? And how to actually defend against these threats when you go for your cybersecurity interviews. So the threat is a man in the middle and SSL stripping. If an attacker can trick your browser into accepting a rogue certificate, they can decrypt and view your traffic. Another vulnerability, weak cipher suites. Attackers look for servers that still support outdated broken protocols like SSL-v3, TLS 1.0, or weak ciphers like RC4 or 3DES. They can exploit known vulnerabilities like Beast, Poodle, or Sweet32 to decrypt the session. So this is also useful for if you're doing capture the flags and bug bounties as well. The defense, forward secrecy, PFS. Modern TLS uses ephemeral keys, the E in ECDHE. This means a unique key is generated for every single session. Even if an attacker steals Google's private key, master key in the future, they cannot decrypt past traffic they captured over the network. I deep dived more into this in the Diffie-Hellman video. And this diagram also sort of goes over the handshake example, the TLS handshake, different from the three-way handshake. So we have the client hello, then we receive the server hello with a certificate and a server key exchange and a server hello done. Then in round 2, we send back the client key exchange and the cipher spec finished. Then we get the change cipher spec finished as well on the web server side. A secure encrypted connection is established. So TCP is establishing the connection, and TLS is the encryption of that secure channel. Now we move on to layer 3. This layer handles a logical addressing and routing packets across different global networks. So we have IP routing and BGP. The routing process, packetization. Layer 3 appends an IP header to the data, which includes your local source IP, Google's destination IP, retrieved back in layer 5. Your device checks its local routing table, seeing that the destination IP is outside the local network. It forwards the packets to your default gateway, your home or office router. Border gateway control. Once on the public internet routers owned by different ISPs, use BGP to communicate with each other. BGP acts as the internet's GPS, constantly calculating the most efficient path through various autonomous systems to deliver your packets to Google's infrastructure. If you want a refresher on network layer 3, again, I had that video. We have encapsulation occurring at layers 3 and 2 rather, and layer 4 as well. Oops. So maybe a refresher on that as well. Then we also on layer 3 we have network firewalls and ACLs on this layer. So security revolves around verifying identities at the IP level at layer 3 and protecting routing infrastructure from being misdirected. So the threat, BGP hijacking. BGP relies heavily on trust. If a malicious or misconfigured ISP falsely advertises that they own Google's IP range, routers around the world will start sending Google.com traffic to the attacker's network instead. This allows attackers to intercept, drop, or inspect massive amounts of traffic. Another threat, IP spoofing. Attackers forge the source IP header in a packet to make it look like it originated from a trusted internal device. This is commonly used to bypass basic firewall rules or to mask the true origin of a distributed denial of service attack. The defense, stateless firewalls and access control lists. Network firewalls operate this layer because inspecting packet headers. They use access control lists to block or allow traffic based strictly on source/destination IP addresses and protocols, dropping unauthorized traffic at the perimeter. In my most recent video to this one, where I set up a network topology, I included how to set up ACLs as well. So if you're on a tangent and want to see how do you actually set up ACLs over routers and switches, then you can watch that video as well. After layer 3, we then move on to the data link layer. This layer handles physical node-to-node framing and error detection on the immediate local network. MAC addressing and ARP. The hop-by-hop delivery, encapsulation. Your network card takes the layer 3 IP packet and adds a layer 2 header and trailer, creating an Ethernet frame or Wi-Fi frame. This header contains your device's physical source MAC and destination MAC of the next immediate jump, your local router. ARP, address routing protocol. If your computer knows the router's IP address but doesn't know its physical MAC address, it broadcasts an ARP request. And this asks, who has the router's IP? Tell me your MAC address. The router replies and your computer caches this in its local ARP table. The switch's job. Local network switches read the destination MAC address on incoming frames and forward them directly to the specific physical port where the device is plugged in. Layer 2 security is all about internal localized threats. If an attacker has gained access to your physical office or local Wi-Fi, this is where they will play. Threat, ARP poisoning/spoofing. Because standard ARP has no authentication, an attacker in your local network can send forged ARP replies to your machine saying, I'm the default user. Your computer will update its ARP cache and blindly send all your google.com layer 2 frames directly to the attacker's MAC address. This allows them to execute a local man-in-the-middle attack, which we briefly touched on before as well. MAC flooding. An attacker sends thousands of fake MAC addresses to a network switch. This overflows the switch's CAM, content addressable memory table. When the table is full, the switch fails securely by turning into a dumb hub, meaning it starts broadcasting all the network traffics to a single port, allowing the attacker to sniff everyone's data. The defense, dynamic ARP inspection, DAI, and port security. Enterprise switches prevent these attacks by tracking IP to MAC assignments and dropping fraudulent ARP packets. Port security limits the number of valid MAC addresses allowed on a single physical switch port. Next, we go to layer 1, the physical layer. This layer transmits raw bit stream over physical mediums like electrical, optical, or radio signals, fiber optic cables, and ISP infrastructure. The physical journey. Signal conversion. Your device's network interface card, NIC, converts the layer 2 data frames into signals compatible with your physical connection. If you're on Wi-Fi, it modulates the bits into radio waves. If you're on an Ethernet cable, it converts them into electrical voltage pulses over copper wires. Global backbone. Once the signal leaves your house or office, it travels to your internet service provider's routing facility. From there, to reach Google's massive data centers, your bits are converted into light pulses and shot through fiber optic cables. This includes massive transoceanic undersea fiber optic cables laid on the ocean floor, believe it or not, moving your data across continents at roughly 200,000 kilometers per second. The speed of light in glass, which is kind of crazy if you think about it. Physical security and data center access controls. The defense. Physical security and encryption. The primary defense here is physical access control, interlocking doors, man traps, biometric scanners, armed security at data centers, and strictly guarded network closets. Because physical mediums can never be 100% immune to interception, we rely heavily on the higher layers, layer 6 TLS encryption, to ensure that even if someone physically taps the wire, they only see the unreadable garbage data. So yeah, in another interview I did, they talked about how they were setting up a data center and the different ways to protect it. So this is also really good as well. So I could do a video on that as well. But yeah, there are things like the actual physical protection of the data centers, and then yes, the layer 6, layer 5, the layer 7 protection methods as well. Finally, the very last thing is it comes back to the application layer, the final processing layer where the server responds and the browser interprets secure application data. The HTTP request and server processing. The HTTP GET request. Once the TLS session is established, your browser sends an encrypted HTTP request, get HTTP/2. This packet contains headers specifying your language, browser type, and cookie data. Load balancers and edge security. The request hits Google's edge infrastructure. A load balancer routes the request to a healthy optimal server, while a WAF, web application firewall, inspects the raw HTTP payload to ensure it doesn't contain malicious patterns like SQL injections or directory transversal attempts. The response. Google's application server processes the request and returns an encrypted HTTP response containing a 200 OK status code alongside the raw HTML, CSS, and JavaScript files. Rendering and CSP protection, the grand finale. Passing the DOM. DOM stands for Document Object Model. The browser receives the raw HTML and constructs the DOM tree to map out the structure of the page. Executing JavaScript. The browser's engine executes the JavaScript files to make the page interactive and paints the pixels into your monitor. That's it. That was a lot. I think this video has gone for nearly half an hour, but I wanted to make sure I covered everything so that if you really wanted to deep dive into the specific contents, then you could, but I recommend you, specifically this right-hand side, you just remember the key headings, so you can just say it, and then if they probe you, you should have enough, if you've watched this video a couple of times, to just say the things that come to your mind will probably most likely be right, and then you can also touch on the attacks and the defense mechanisms as well. Thank you very much for watching. Comment if you want any other specific videos, any changes. If you don't like this format, you want me to go back to edited videos, and leave a like as well if you want to. Thank you very much. Have a nice day.